Hi, I'm Mijinan from Sungkyunkwan University. Today I'll be presenting our work, the Write After Read protocol, which is a collaboration between Sungkyunkwan University, Hanyang University, and Samsung Electronics. Flash memory-based SSDs are widely used in computer systems. It's because SSD shows very fast read and write speeds, and its multi-channel architecture provides high internal parallelism. Also, because of the nature of NAND flash memory, the cost of a write operation is much higher than that of a read operation. In addition, the price per capacity of SSD has dropped, so many data centers use SSD for low latency and high throughput. However, simply adopting SSDs for DBMSs cannot fully exploit their performance. As mentioned earlier, Flash SSD has one characteristic distinguishable from hard disk. It is the asymmetry in read and write speeds. As shown in the blue area of the table, the read speed of SSD is up to 13 times faster than the write speed. On the other hand, hard disk shows nearly identical read and write speeds. In summary, while the asymmetry ratio varies depending on vendors, it is an intrinsic characteristic of SSD. Meanwhile, the buffer manager is at the core of DBMS. In particular, read performance is a crucial factor of overall performance for DBMS. It's because synchronous read latency determines transaction performance. One common scheme tightly involved with this is the read after write protocol. On a page miss, when no free or clean pages are available, the buffer manager will choose a victim page based on its replacement policy. It will first clean the frame by writing the dirty victim to the storage, and then read the missing page from the storage into the cleaned frame. In this situation, a read request is blocked by a write request, which we call a read store. But then, why do write and read need to be serialized? It's because two I/O operations share one buffer frame. It contains the dirty page to write, and at the same time the missing page will be fetched into this frame. This strict I/O ordering prevents the system from fully utilizing the parallelism of SSD. Also, in principle, the synchronous read should be in the critical path of the ongoing transaction. However, on read stores, the wrong write latency is added to the critical path of a page read. As a result, although writes in the database are asynchronous in nature with the help of the while log, the total read latency becomes severely prolonged. So, to check the frequency of read stores in real database systems, we measure the read store ratio on MySQL. As you can see in this table, there is no read store problem in hard disk due to its symmetric I/O speed and absence of parallelism. In other words, there is a balance between the speed of producing free frames and consuming them. However, in SSDs, over 25% of read requests experienced stalls. In addition, even when the buffer cache size increases and the number of read requests accordingly drops, read stalls continue to occur. This is because reads are several times faster than writes, and SSDs also have internal parallelism. That is, though the background writer does its best to flush the dirty pages aggressively, the free frames in the free page list are promptly exhausted by foreground processes. For the same reason, the clean frames at the I/O tail are also consumed quickly. As a result, the speed of producing free frames cannot keep up with the speed of consuming them. In summary, SSDs with asymmetric I/O speeds and parallelism cause significant read store problem when they encounter the raw protocol. As explained previously, a resource conflict between the new page PR and the dirty victim page PW is the main cause of read stores. In fact, PR does not have any relationship with PW. PW happens to be chosen as the victim according to the buffer replacement policy. However, because of the shared buffer frame, they have to be serialized. This lead store problem eventually lowers the CPU utilization. Also, the write and read serialization does not fully utilize the parallelism of SSD. Although two requests can be directed to the different channel inside SSD and handled in parallel, their serialization at the database buffer layer prevents parallel processing in storage. Finally, read stores at the right time to the critical path of the transaction, so transaction latency increases significantly. In fact, except for resource sharing, there is no compelling reason to guarantee the I/O order. And interestingly, the read store resembles the structural hazard in computer architecture, which is usually avoided by replicating conflict resources. This recognition led us to replicate memory resources for writes into a small additional memory space. And as we will see soon, this memory space enables read after copy rather than read after write. This is the architecture of our solution, the write after read protocol. We introduce a separate memory space for writes called the temporary write buffer. Its role is to temporarily store the dirty victim pages and make the shared resources available for reads. Now let me explain how a read request is handled under the write after read protocol. On a page miss, the foreground process tries to obtain an available frame likewise in the raw protocol. If it fails, it copies 30 pages at LRU tail as many as LRU scan depth into the temporary write buffer. Then it cleans those frames and returns them to the free list immediately. Therefore, WAR can generate free frames much faster than raw, in fact almost instantly. Then the process can read in the missing page using one of the freed frames. And since many free frames are now available in the free list, other foreground processes can get free frames without store. Meanwhile, all the dirty pages in TWB will be asynchronously written to the storage in a batch by the background writer. So we call this protocol the write after read protocol. For consistency and recoverability, every page copied to TWB writes the write-ahead log that is while log. For this reason, the reversed order of read and write does not cause any database consistency problem. To summarize, by replicating memory resources for writes into the temporary write buffer, WAR resolves resource conflicts and avoids read stores. This simple difference makes a huge impact on I/O and CPU utilization on top of read fast but write slow flash storage. The WAR protocol provides 4 major benefits. First, WAR can proceed reads and no store with the help of the temporary write buffer. Second, WAR can reduce the transaction latency because it only adds short memory copy time to the critical path of the transaction. Third, WAR can issue writes and reads in parallel, so it can better utilize the parallelism in SSD. Finally, the high CPU utilization and denser I/O patterns increase the overall system throughput. Now let's see evaluation results. We implemented WAR on MySQL, and by default we set the database size to be 200 GB and the buffer cache size to be 10% of the total database size. We evaluated the WAR protocol using a set of popular OLTP workloads. For fair comparisons, we allocated the same amount of extra memory to RAW as an extended memory space for buffer cache and WAR as a temporary write buffer. Let me first clarify the baseline. Many DBMSs have hundreds of configuration knobs to control their runtime behavior. So to investigate the effects of knob tuning on read stores, we adjust I/O performance critical knobs in MySQL. This figure shows the transaction throughput of TPCC. As you can see in the figure, knob tuning improves the throughput and reduces read stores compared to the untuned row. The read-store ratio remains still high, but we use it as a baseline because knob tuning is typical for data-intensive applications. In addition, to see if further increasing the flushing activity alleviates the read-store problem, we signal the background writer to flush 30 pages earlier before the read store happens. This smart flushing technique achieves better throughput than the knob tuning, but still undergoes a lot of read stores. As a result, the read store problem is difficult to mitigate without changing the intrinsic structure of row. In contrast, the WAR protocol avoids read stores, so it can outperform any of the row-based techniques. Next, we measure the transaction throughput of TPCC on different SSDs while changing the buffer sizes. As clearly shown in the figures, regardless of flash SSD types and buffer sizes, WAR consistently outperforms RAW. The IOPS, bandwidth, and CPU realization of each protocol are also consistent with the transaction throughput. The following result is the transaction latency measured by Sysbench. As shown in the figure, WAR improves the average latency and tail latency compared to the RAW protocol. This is because, as mentioned earlier, the WAR protocol can avoid wrong write latency in the critical path of the transaction. Next, to see how the degree of parallelism affects the WAR protocol, we measured the TPCC throughput while changing the number of available channels in SSD. As shown in the figure, WAR works well with parallelism. But without parallelism, WAR does not provide any performance gain. This result shows that the degree of parallelism is important to WAR. And therefore, on SSD with abundant parallelism, WAR can leverage this parallelism and reliably deliver performance benefits over the RAW protocol. So, in conclusion, this paper elaborates on why the existing RAW protocol causes the read store problem on SSD. Then we propose a simple but effective solution, the WAR protocol. Given its simplicity, applicability, and effectiveness, WAR can be a practical buffer management solution for flash storage. For more details about our work, please check out the full paper. Thank you.